This is a Nordic-baltic physics Olympiad problem. All the credit goes to Paivo Simpson. I hope I pronounced that correctly. We've got 4 charged particles, one at each corner of a square. Each has a velocity, just like this. The first part of the problem goes like this. After a long time has passed, what is the magnitude of the final velocity, v of f, of the particles with respect to the center of mass of the system?
All right, let's get to solving the problem. So we have to find this final velocity, v of f. Let's write that down. There's a lot of going on. There are velocities, masses, charges, and this geometric shape, and just a lot of variables. So what can we do to find this final velocity v of f? The most important part to understand about Olympiads and just tough questions in general is that you have to use some sort of physics idea to find your variables. Usually it's going to be something like momentum or energy. Sometimes you have to use areas or geometric shapes to figure stuff out, which is also what we're going to do this time. So the most important idea that we're going to use here are energies. I think it's going to be really useful to understand that while these particles are together, they're going to have some energy that is going to be a combination of kinetic and potential energies. But once they go apart, because they're the same charges, they're going to be repulsive and they're going to fly apart. Then they're going to have no potential energy once they're infinitely far away. They're only going to have this kinetic energy. By equating the starting energy with the ending energy, I'm going to show you that we can actually find our ending velocity. So I'm going to start the problem by just finding the expression that tells us how much energy we have in the beginning of the system. So as I said, at the beginning, we have 2 kinds of energies. We have kinetic energy because the particle has a mass and velocity, because these particles have charges, and these charges are repulsive one to another. Because of this repulsion, this force that's acting on them, they also have electrical potential energy. So let me just open these expressions a little bit. Here I opened up the potential energy formula. You might see that it's kind of weird looking. If we only had one particle that's moving in the system, I would definitely just write it down as this and also include the 1/2, obviously. That's not the case here. Because we have 4 particles, all of them are moving, we have to consider the total system energy. That's why I have to sum up all the potential energies within the system. That's why I write this down. If you're afraid of working with something like this, don't be, it's really simple. Let me open up the expression even further. Okay, so let me show you how I'm going to use this big formula. I see that this particle up here has 1 particle that's on its left and 1 particle on its right, equally far away at the distance L. So we can just lump them 2 in the same formula. We also know that the charge of each particle is Q. So that's why we can just skip this Qi, Qj, and just write it as Q squared, because we have to multiply the same charges together. So in the end, it just becomes. So this is the expression. Of course, we can just write this down as 4, but let's not forget, we also have to take into consideration the particle opposite of it, okay? Each particle has 1 particle that's opposite of it acting on it. So we have to write 4 times 1/2. The top doesn't change, it's still the same charges. But what's this distance? Because we know the side lengths are L, how can you find this diagonal? If we know that this angle has to be 45 degrees and this is the length of L, then using sine for 45 degrees, we find that this length right here has to be square root of 2 times L over 2. And we have 2 of these, 1 above, 1 below. If we add them up, we get the diagonal. And it should be the square root of 2 times L. Hopefully that made sense. So the last thing we should do is just simplify this expression. And this is our final expression. And one thing we can note here, the further the particles move out, the more L tends to infinity, and actually this term goes to 0. And we see that the total energy at the end just has to be this expression right here. So let me rewrite the final energy as the kinetic energy that the particle will have at the end. That's our expression for the energy at the end. Don't forget to change this velocity from v0, because it's not the initial, it's the final velocity, vf. Now we just have to equate the total energy at the beginning is the same as the total energy at the end, and then we can find this total velocity at the end, v of f. Okay, now that it's written out, we just have to find the final velocity and solve for it, okay? And it becomes just algebra. And this is the expression for our final velocity. Let's see if we have all the variables that were given to us by the task. So we have this initial velocity v0 that's given. The charges are given, the mass is given, we know the distances at the beginning, and the rest of these are just constants and numbers. So that's our problem 1 solved. It's important to reflect on the problem and see what we did to come to the conclusion and the solution of this problem. So what we did here is we found this total energy at the beginning of the problem. So once these particles flew off to infinity, their total energy went from kinetic and potential energy sums to just kinetic energy. This idea that the energy does not change throughout movement is very often used in problems in physics. You have to get used to equating the energy at the beginning to the energy at the end. From those expressions, you can usually find 1 or 2 variables, just depending on how many equations or systems of equations you have. I think this example did a pretty good job of showcasing this strategy. Okay, on to part 2.